This is part 6 for the module 11 lecture. In this part, we're going to talk about the inferences about the slope parameter. Let's see. All right. So if you remember from what we've done before, when we talk about estimation, we talk about testing a hypothesis and calculating a confidence interval. So in this case, we're going to test a hypothesis about the slope parameter, and later on I'll show you how we calculate the confidence interval for this slope parameter. Now, the least squares estimates, lowercase a and lowercase b, are used as the basis to make inferences about the parameters a and b. And our interest is to see if these parameters are non-zero. And now you recall that the magnitude of the parameter b determines how much the variable x increases or decreases the mean of the variable y. So if b is equal to 0, then x has no effect on the response variable. Now, if the magnitude of the parameter a just gives us the point where the line will intersect the vertical axis, so that is the average value of y when x is equal to 0. But that doesn't tell us anything about how x affects y. So really, the inference of interest is about the slope parameter, because that one tells us whether x affects y and how much it affects the average of y. All right, so our inference is going to be focused just on the slope. Right, so in here, we want to see if x influences y. So in that case, we want to test the null hypothesis that the coefficient, or rather that the x variable has no impact on the y variable, which is equivalent to say that the slope is equal to 0, because if the slope is 0, we have a horizontal line. So here's y and here's x, and there's a horizontal line parallel to x. So it's telling us that y can vary any way it wants as x is changing. So x does not affect y. All right, and we test that versus the alternative hypothesis that the slope parameter is not 0. In other words, x affects y. And this is a two-tailed test. All right, so what are the consequences of not rejecting the null hypothesis? Well, if you say that the parameter is equal to 0, that means that, as I said earlier, the line is parallel to the x-axis. X does not affect y. Or you could have a situation where the correlation, the slope, the line is still horizontal with a 0 slope, but there is an actual relationship, but it's just not linear. Or if you do not reject the null hypothesis. If you reject the null hypothesis, in other words, you say that the slope is not 0, well, you may have a positive relationship between x and y, or a negative relation between x and y, or you can still have, like in this case, a positive relationship, but is not the correct model because there is some curvature in the data. But this is what happens when you don't reject the null hypothesis and when you reject the null hypothesis. All right, so in order to proceed to test the hypothesis, we need to determine the sampling distribution of the statistic b, in other words, the estimate of the slope parameter. So since random errors are assumed to be independent, then the mean of the sampling distribution of b is mu sub b, and its standard deviation is given by this equation. Also, the random errors are assumed to follow a normal distribution. Therefore, we can say that the sampling distribution of b is normal with mean mu sub b and sigma b for its standard deviation. All right, but however, to test the null hypothesis that b is equal to 0, the test statistic is defined as this, where we're using S sub e, which is the standard deviation of the residuals. Now, under the null hypothesis, b is equal to 0. Therefore, the test statistic simplifies to this equation, where I just move the sum of squares of the x, the square root of the sum of squares of the x to the numerator. So, but the equation with b equal to 0 then we can write the test statistic like this. All right, so we determined that the sampling distribution of B is normal. Also, we are saying that we're replacing the population standard deviation of the random error, or rather of the sampling, the standard deviation of the sampling distribution of B with its estimate, which is the standard deviation of the residuals, because we are replacing this population standard deviation with a sample standard deviation, and we have a normal sampling distribution. Then we can say that the t distribution is applicable, in this case with n-2 degrees of freedom. All right, now if you are asked to follow that critical value approach, then to establish the rejection regions, then because this is a two-tailed test, and we know we have the lower and upper rejection regions, and we divide alpha by 2, and we use the degrees of freedom in table 5 to find the upper critical value. And then we use the symmetry of the t distribution to find the lower value, which is just the negative value of the upper value. Then if the t observed, the value of the test statistic, falls in the rejection, in either rejection region, we reject the null hypothesis. So this is the same rule that we have been using since module 8. All right, if you're asked to use the p-value approach, then remember this is a two-tailed test, so the p-value is 2 times the probability to the right of the t observed. And again, from table 5, we can find some bounds for the p-value, but if you want to find the exact p-value, you can use this formula in Excel. And the same rule as before. If the p-value is less than alpha, we reject the null hypothesis. So that hasn't changed. All right. The other inference that we can make is calculating the confidence interval for the slope parameter. And that's given by these two equations. So this is the equation for a lower confidence interval limit, and this is the equation for the upper confidence interval limit, where we will rely on the value of B that we calculated earlier. And this T alpha over 2 is found in table 5 for alpha divided by 2 and for degrees of freedom of n-2. Now, we're using the T distribution because the random errors for any value of x are independent, normally distributed with mean 0 and constant variance. And this constant variance is estimated with the standard deviation of the residuals. So the T distribution with n-2 degrees of freedom can be used for calculating the confidence interval limits. So again, whenever we want to calculate confidence interval limits, we need to justify the use of the distribution. All right, so now with this, then in the next recording, we will solve a problem where we test the hypothesis for the slope parameter and we calculate its confidence interval limit.